All right, ladies and gentlemen, today's class recording has started. So, yesterday we talked about describing waves, and we talked about a couple characteristics of waves, and what are some things that we can use to describe a wave? What are some of the terms that, let's back it up 2 days. Wednesday we introduced waves. What are waves? Disturbance. What do waves do? Transfer energy, okay? So, then describing those waves, right? We introduced a couple terms yesterday, so let's talk about some of those terms, right? What is one thing we introduced yesterday? Joanna, go ahead. Wavelength. What does wavelength tell us? Distance between two waves, okay? That's wavelength. What else? Amplitude. What does the amplitude tell us, Joe? So how tall that wave is, right? But more importantly, what does amplitude tell us about that wave? Yes, it tells us how tall it is, but what does that tell us about the wave? So the amplitude tells us about the energy that it carries, right? All right, what else did we talk about? Two terms that are pretty closely related to one another. Period and frequency. And they tell us basically how often a wave happens, right? The last thing we talked about yesterday was wave speed. What does the wave speed depend on? Frequency and wavelength, but actually more importantly, it depends on something else. What does the speed of the wave depend on? Could depend on those things. That's how we calculate them, but what does that speed actually depend on? The medium that it's traveling through, right? That waves will travel at different speeds through different mediums. And we'll talk a little bit about that today when we talk about refraction, okay? All right, so that being the case, now we know about what waves are. Now we know about how we describe waves. Today we talk about how waves behave and how they interact, because it's different than what happens when matter interacts, because it's not matter, it's energy, all right? So let's talk about what happens when a wave encounters a new medium. 3 things could happen when a wave encounters a different medium, all right? So let's talk about what 3 things could happen. So the first thing that can happen is called reflection, all right? And like its name suggests, when a wave bounces off of a surface that it can't pass through, all right? So today, just like yesterday, there's a couple videos I wanted to show you, or some clips of videos that illustrate these concepts, all right? So let's go here to not this video, but this video here. Okay. All right. I'm going to mute because I don't like this guy's voice, but you know, whatever. Actually, he's talking to his class. So, yeah. All right. This is what we call a wave table, which is a little bit different than the wave table from yesterday. I wouldn't call this a wave table, but it is something that's used to demonstrate wave behavior. Okay. So these little sticks here, they all have like a little axle that they sit on, and they can swivel side to side. Can you see that they're sort of like moving a little bit here? Okay. So, and that's all fine and dandy. Oop, I should maybe get this out of the way. Okay. And that's all fine and dandy, but I can see those waves a little bit more, right? Okay. So first, you can hopefully you can tell just from this little demonstration right here, what kind of waves are we going to be using to demonstrate here? These are definitely transverse waves, right? The medium, the sticks, are moving up and down as that wave is moving side to side, okay? And I talked right over the first demonstration that I wanted to show you, so I'll back it up a little bit here. All right, so in order to create a wave, what do we need to have? A disturbance, and that disturbance has to do what? Work, right? Does the teacher apply a force to the very first pole? Does the pole move because of that force? Yep, that's work, right? So he's going to do some work here. He's going to create a wave, and that wave is going to travel through the medium, one stick disturbing the next, until it gets to the end right here, right? So what happens when it gets to the very, very last stick? It bounces back, right? One thing that we didn't talk about, but we will here in just a second, okay, is... So if you look here at the end, oh, I gotta move my thing, right? If you look here at the end, see this little stick that he put right here? It keeps the last one in place so it doesn't move up and down, all right? So it reaches the wave reaches a medium that it can't pass through, and so it reflects off of that medium and comes back. All right? Good there? And then when it gets back to the other side on the far right, what did you notice with that wave? Not too far. All right. Here we go. Ready? Do it again. There we go. All right. Bounce. And then what happens at the other end? Does it bounce again? Yeah, it bounces again, right? Because it hits the end of the medium, the sticks, and it can't go into the air, so it just keeps going, it bounces off of that and goes back the other way. All right? So, a couple things about reflection. Pause that for a second. Randall. So, I never heard of Randall before. All right, so a reflected wave has the same speed, frequency, and wavelength. But sometimes we will see a change in the amplitude. Actually, sorry. Sometimes we'll see two changes in amplitude. Okay? So here is a picture that shows basically the same thing we were doing on Wednesday with the big slinky, right? So here, right, we have a wave, and I should have flipped this around. This wave is actually going towards your left. It hits the end, and then it bounces back in the other direction. Okay? Good there? All right. Amplitude-wise, what do we notice about the amplitude of this wave? There's two things you could tell me about the amplitude of this wave. It's lower, right? So what does that mean is happening to the energy? It's decreasing, all right? Second, what else do you see about that amplitude? Who wasn't even here yesterday? So let's look at the wave going in versus the wave coming out. It's flipped, right? On the way in, the amplitude is on the upper side of the spring, but after that reflection, it's on the lower side of the spring. All right? So, first two things, right? Okay. This is what we call a fixed end reflection. Okay? And you have this picture over on the right-hand side of those slides on your sheet over there, okay? A fixed end means that it's stuck in place, just like the end of the wavetable that we saw in the video, okay? And when that happens, we find that the amplitude is flipped over onto the other side. But the other thing that happens, no matter what kind of reflection we talk about, is that the amplitude is lower. We've talked about that a lower amplitude means what's happening with that wave, or what's different about that wave. It's losing energy. Why does it lose energy? Friction. It's like the best answer ever, right? Yes, one part of the medium moves another part of the medium, moves another part of the medium, but in something like this, right? One stick makes the next stick move, makes the next stick move, but what does it run into as it's moving up and down? Air. And friction takes that energy of the wave, right, and turns it into what? Heat. Jack's on the roll today. Not that that's a surprise. But. Frank, go ahead.
So eventually it'll stop.
Because eventually what happens? It loses all that energy, and then the wave doesn't exist anymore, right? Same thing with sound waves, right? When I'm closer to you, it's louder, right? Because that sound wave is carrying more energy, the amplitude is bigger. But as I move farther away from you, and the wave has to travel farther and farther through the air, it's losing more and more energy to the air, and so the amplitude of the waves is lower, and from a sound standpoint, we call that not as loud. Does that make sense? Eventually, the amplitude decreases so much that there's no more energy anymore, and then you can't hear me. Does that make sense? Okay. So the idea of the lower amplitude, or the amplitude decreasing as that wave travels, we refer to as damping. D-A-M-P-I-N-G. All right? So where it says amplitude is usually lower, why? Why is it lower? What's happening to the energy of the wave? It's losing energy, basically to what? Friction, right? And we refer to that concept of the wave losing energy to friction as damping. Okay? All right. Good there? You okay with that? All right. Next thing on reflection, I'm going to switch videos here. And I'm going to go to this sweet video, all right? Which I believe, when I looked up, is from like 1983. All right, so. All right, so here, this is another water table like we were looking at yesterday. We're just looking at it from above instead of from below. Okay, this is what it looks like. Here's the little arm that just goes up and down, up and down, up and down. It hits the water, creates disturbances, makes wave in those disturbances. Okay, good there?
What's the thing on the right?
The thing on the right is just something solid, and you'll see that in just a second. Okay, so like I said, he only talks for like the first 20 seconds of the video. So here, I'll show you. Okay, here we go. Look at this. Look at those sweet graphics of water waves, like So, yeah. That's all right. So this is the only talking in the video.
This video shows the standard wave effect can be seen using a little band. There is no commentary during the rest of this video, but the shot numbers shown on screen correspond with the description in the teacher's notes.
All right. So look at these sweet graphics, like from 1983. So, all right. So here we go. All right. Okay. All right, so what happens to those waves when they hit that solid barrier? They bounce off of them, right? Now, this is a little different than the bouncing off of the solid barrier that we saw in the first video, because we're not hitting that barrier straight on, right? We're at an angle. So the waves come in at an angle and they go out at an angle, all right? And actually, they froze it right there. So you can see that the waves come in this way and go out this way, all right? And what we find is that when waves reflect in that manner, the law of reflection states that when an angle comes in, it's going to go back out at exactly the same angle. So just like, and this applies even not even to waves, but to other things too, right? If you've ever played billiards before, right? If you play pool, depending on how you hit the wall, that's going to determine the angle that the ball comes out. Now, you can also like put spin on it to change that, but if it's just coming in, it's going to go out at the same angle. So we say that the angle of incidence, what it's going to when it comes in, is equal to the angle of reflection when it's going out. Frank, good.
So if there's like a tsunami, the only reason that like it destroys the building is because of wave one.
So now let's talk about what else can happen. Okay? So reflection happens when a wave hits something that it can't go through. Okay? But sometimes waves encounter a new medium and they can keep going. Now we learned yesterday that if that wave goes into the new medium, what changes? The speed changes, right? But the wave will still go through it. Okay? So let's take a look here at this demonstration. Going back to this guy here.
Okay.
And we're going to fast forward to right around here. Okay, so let's see, wait till he gets out of the way. Oh, I should show you this first, right? All right, so here, oh crud. So in this case, he takes the little he takes the little stand thing and he puts it right in the middle. And you might be able to guess that when the new wave hits that stand, what's going to happen?
Brick wall.
Basically, yes. All right, so we'll wait patiently here. Right, and it reflects off of there. Okay, and that's again fixed end reflection. So we flip the amplitude over to the other side, right? If you watch closely. All right. No. Come on. Subscribers.
Oh, did you speed it up or video off?
Oh, I didn't. Maybe I'll do it at the end. All right. So here, amplitude is pointing upward, right?
Yeah.
But then, after it hits the boundary,
Oh, it's going down.
right, now it's downward. Okay? But it still bounces. Okay? All right. The next part, though, Frank, go ahead.
So with the amplitude thing, like, with air resistance is losing energy. So does that mean if there was no air resistance, I could hear you from a mile away?
Good question, Frank. All right. So, Frank says sound waves lose energy to air resistance as they travel through the air. Right? So Frank says if there was no air resistance, does that mean he could hear me from a mile away?
Oh my God, it's this.
Alex says no. Air resistance. That doesn't, see, if you're deaf, that doesn't mean there aren't waves hitting your ear, though. That means you can hear them. Right? So, Frank says if there's no air resistance, does that mean he could hear me from a mile away?
As long as like you're in a big field.
Oh, good.
And so the reason if something does come far away, it's fine because the air resistance
Doesn't slow the wave down. What does the air resistance do? Dilutes it, spreads it
Damps
out,
it.
and also damps it. It decreases the amplitude. All right? But, let's go. Christina. Other things absorb it, can absorb. That's on, actually, we're going to talk about absorption here in just a second, okay? But going back to Frank's original question, if there was no air resistance, could you hear me from a mile away?
Yes.
No.
Come on, Chris.
So, and here, Frank, this is kind of a technicality, all right? If there's no air resistance, what does that mean? There's no air. There's no medium, all right? So, Frank, right, in space, astronauts can't yell to each other, right? Because what is there in between one astronaut and the next astronaut? Nothing, right? So that's kind of a trick question, right? If there was no air resistance, yeah, it wouldn't lose energy, but there's no medium to carry the wave, so we can't do that, right? So we have to use different kinds of waves called electromagnetic waves, which we're not going to talk about.
Yeah, it's on this paper.
I know, I decided I wasn't going to talk about it, so. All right, so next setup here, okay? This guy, Randall Dupree, I'm assuming this is Randall.
I guess it doesn't say subscribe, you only have to say
Yeah.
subscribers.
He doesn't advertise.
You gotta do
apparently.
an intro and an outro.
That's right. So.
Outro.
And then run a promo, you know, like so.
What the giveaway?
All right. In this case here, he takes a little cup filled with water and hangs it on one of the sticks. So it's not rigid, but does make that stick heavier. All right. So let's watch here and see what happens. If I remember correctly, I can fast forward here.
Wait, that cup's hanging right now?
Yep, that cup is like it's filled with water, but there's a string attached to one of the sticks. Okay.
Is it touching the thing or no?
It is.
Oh,
Okay.
Oh no.
All right. So here's the wave. Okay. All right. Okay.
Oh.
So you guys saw the cup goes up, right? All right? Did the wave pass through the stick that had the cup hanging on it?
Yes.
Yeah, it did. All right? So that's not reflection, but actually, all right, it gets into a little thing, okay? If you look, now there's almost two waves. Do you see them? Right? One wave is still going to the left, but what do you see about this wave compared to the wave before it ran into that stick?
Opposite.
Well, what about this one right here?
It's lower.
It's lower amplitude, right? And then here, so what happened when the wave hit that stick that had the water? Reflection happened. That's this one right here, but some of it went through, and we call that transmission. But does it have the same energy?
Yes.
Does it have less amplitude? Be confident. Yeah, it does, right? So those waves don't have the same energy as the original wave. What if we added up their amplitudes? Should we have the same energy?
Yes.
The water takes a little bit of it, right? And friction and some other things too, right? We still conserve energy, but we're losing some of it to some other stuff. Oh, go ahead.
Is it having like something on the other side too?
No, it's just on the one side. So.
Would that make it harder for one side to go up if you do
The sticks are rigid. So if you affect one side of it, you're basically affecting the other side of it. You know what I'm saying? Like it's kind of like a seesaw. You know, if you put somebody really heavy on one side, the whole thing's going to tip that way. You know what I'm saying? It's not just the one side that's going to tip that way. You know?
easier for it to go down and not back up?
Yes, and that's kind of the point, is that we want to lose some of the energy that it was traveling along the way. All right? So, sometimes, instead of being reflected, all right, we will have a little bit of absorption, where it loses some of that energy. All right? Also, sometimes we pass through, and it changes, but not enough to stop it. And we call that refraction. Okay? All right, so refraction. Refraction is when a wave bends because it gets a new speed as it enters a new medium. Refraction occurs when one part of a wave moves at a different speed than the other side. All right. How many of us are unfortunate enough at our house that we have to cut the grass?
Yeah,
Okay. If your dad doesn't let you, then you don't have to cut the grass. Oh, you want to do it? Okay. So.
Yeah, right.
How many people have to use the push mower? All right. So, tricky part of cutting the grass is when you're right on the edge and you got one set of wheels on the sidewalk and the other set of wheels in the grass, right? Especially like in the springtime when the grass is like really, really thick. Right? Well, but you have one set of wheels where it's real easy to move, but the other set of wheels where it's kind of harder to move, right? And that causes the lawnmower to try and bend because one side's moving faster than the other side. That's what happens in this refraction. That when the wave hits a different medium, like in this case the glass, it slows down. But only the part of the wave that's in the glass slows down. The other part of the wave is still traveling exactly the same speed as it was before. So we get that bending because one part's trying to go fast and one part's trying to go slow. All right? Classic example of refraction is something Zac Efron's abs. All right, so, but it's not what I was actually showing you. All right, or you know, it's this picture right here of this polar bear. All right. The fact that it's a polar bear is kind of cool, but more importantly, what are you seeing? Right, the body, or his back, is not connected to the rest of it, right? Or it doesn't look like it. Or maybe you've seen where you have a pencil that sits in a glass of water, right? And it doesn't look like the pencil is connected, right? It's not that it's not that moving the pencil into the water changes the pencil. There's Zac Efron's abs again. So, okay. But, let me do this real quick. All right, there we go. It's not so much that the polar bear is different under the water as it is above the water, but the waves bend as those waves go out of the water and into the air, right? Swimming pool in the summertime, right? Sometimes because you're bored or whatever it is, there's little diving rings, you throw them into the pool, and then you have to go and get them, right? Okay? So you stand on the edge of the pool, and you're like, all right, there's the diving ring. You dive at the diving ring, but you get to the bottom, and what happened? It's not there, right? Because those waves bend as they come out of the water, and it makes it seem like the object is in a different place, but really those waves are just bending as they come out, and it makes it look like it's in a different place than it is. So if you're ever on a desert island, or you get stranded on an island, and you have to spear fish, right? Because I know it's probably going to happen to you sometimes, so. But if it does, you can say oh yeah, I remember this from physical science class, right? And so if you have to spear fish, and you see that fish in the water, don't throw the spear at the fish. It's not there, all right? It's actually a little closer to you, so throw it like that.
Closer or farther?
Closer. So, I did say closer, but I could tell you how it's closer, but it's a little bit more than I wanted to get into today. So it gets into which way does it bend when it goes from water to the air, and at this point, as long as you get that it actually bends, I'm cool with that. All right. Okay. So that's refraction. Let's skip ahead and let's talk about superposition. Not just regular position, super. So, superposition is one of the things that really distinguishes waves from matter. Okay? Matter will bounce off of things, just like waves do. Okay? Matter will slow down when it encounters another medium. But one thing that matter can't do is have two things in the same place at the same time. Right? Here is a really, really old picture of this kid wearing star pajamas. Kind of what it looks like to me, or maybe it's just a really funky shirt. I can't tell if it's pajamas or just a really funky collared shirt. Okay, but he is projecting a picture of what looks like a field with a bunch of flowers from this projector over here onto the left-hand side. But then this kid, who might be this other kid's twin, I don't know, they have kind of the same haircut. All right, he's projecting a picture of the clouds from bottom to top. The two picture projections pass through each other on the way to their screens. But do they affect each other? No. They don't, right? Superposition means that two waves can occupy the same place at the same time. Why can two waves occupy the same place at the same time? What are waves?
Our disturbance.
What are waves? What are waves made out of? What do waves do? Move. They transfer energy, right? That's how we make a wave, but then it carries energy, right? So why can two waves be in the same place at the same time? Because what are waves? They're energy, right? You can have energy at the same place at the same time, even if it comes from different places. You can't have two matters in the same place at the same time. Frank, did that answer your question? Or
Yeah.
Do you want to answer the question?
Yeah,
Right. Consider, we use this principle all the time. When we have a musical group of some kind, right? As long as it's not a solo, right? You have multiple waves whether they come from two people's voices in a duet, a guitar, a bass, drums, and a keyboard in a rock band, or all the instruments in an orchestra. You have multiple waves being created, but you hear them all at the same time, right? If two waves couldn't be in the same place at the same time, music wouldn't work, right? If the waves got to your ear, but only one of them could go in, right? You'd hear the violins, then you'd hear the bassoons, because you got to have a bassoon in the orchestra, right? And then you'd hear the tuba next, because those waves couldn't be at the same place at the same time. But with waves, they can exist at the same place at the same time because they're energy. So we call that superposition. All right? Two things can happen when we have waves in the same place at the same time. All right? Oh, waves are energy, not matter. Two kinds of energy in the same place at the same time. All right. We have interference. When two waves occupy the same place at the same time, their amplitudes will combine. Yeah?
So if they're both energy and they combine,
Yep.
the law of conservation of energy says energy can't be created or destroyed.
True. But we're not creating or destroying energy, Frank, but we're just experiencing that energy at a certain place at a certain time. Okay? So, here. Alright. Let's go this. Okay. This is real life video taken in this classroom. So
Ooh,
Alright.
am I in it?
No, it's from 2 years ago.
So
No, the kids like graduated 2 years ago. These are seniors from 2 years ago. So yeah, this is regular physics, but all right. So 3. Oh, slow mo.
Slow-mo.
Yeah, slow mo. All right. So here it comes. All right. Maybe. Boss is really slow mo. Okay. Wave 1, wave 2. Do we see them?
Yeah.
Okay. Watch what happens when they run into each other. Okay. Okay. So, did we make new energy, Frank? No, it's just the energies of the two waves that were already there, but now they're in the same place at the same time, so that amplitude is greater at that moment in time. But, as we watch, right, what happens after they run into each other? They just keep going along their merry way, right? This wave was the one that was created by this kid in the yellow, Jimmy. And then this wave here, that was my wave that I created on the other side. I don't remember who videotaped, somebody else in the class. Not Jimmy, because he was making waves. So, all right. Or me, yes. Okay. All right, so there's that. Okay. Let's see about this one. Apparently not slow-mo on this one. Oh. Okay. So, wave, right? Alright. When they meet this time, because they're on opposite sides, we get what we call destructive interference. Okay? Sorry, first one was constructive interference, because we're constructing. Destructive interference. Alright, so there's our wave interactions. Monday we'll play with some slinkies and see these things in action. Good.
The waves are the same place, but one wave it goes that way, and the other way the crest goes that way.
Say that again. I'm sorry, I was distracted by immaturity. People throw the things out.
They're in the same place.
Okay.
But the crests are on opposite sides.
That's what this video is trying to show you. It does do it very good. When they're on the same side, they get bigger. We call that constructive interference. When the waves are on opposite sides, they basically subtract from each other, and we call that destructive interference. Okay? We'll talk a little bit more about that on Monday. Okay?